There are two types of crystalline silicon solar cells, monocrystalline and polycrystalline. Have you ever noticed monocrystalline solar cells have round corners but polycrystalline cells have sharp corners? Why polycrystalline cells have a shattered glass look but monocrystalline doesn't? Or the reason behind solar cells' blue color or grid-like appearance? Never? Okay, now is the time to know why. This is New Physicist. Once you learned about what's happening inside a solar cell factory, all your doubts will be vanished. It all starts with a raw material, which in this case is sand or quartzite, more precisely silicon dioxide, from which we have to extract precious silicon. Silicon is abundantly available, making it the second most available element on Earth. Together with coal or other sources of carbon, the silicon sand is melted down at over 2000 degrees Celsius in an electro-arc furnace. The result is metallurgical silicon with a purity of 99%. The silicon is collected usually in the form of solid rocks. These rocks are being melted together at very high temperatures in a polycrystalline factory, and then to distillation plant, and finally to Siemens factory to get high purity silicon crystals. This process is known as chemical vapor deposition. In Siemens factory, a hot seed rod of silicon is used to get 99.9999% pure polysilicon. Siemens process is very expensive, but other alternatives like fluid bath reactors or blowing gas methods cannot generate this much pure silicon out of metallurgical silicon. The next process is making ingots of silicon. We can either proceed with this pure polysilicon to make polycrystalline ingots, or we follow Czochralski process or float zone process to make monocrystalline silicon ingots. In the process of ingot making, attention is given so that all atoms are perfectly aligned in a desired structure and orientation by controlling temperature and other atmospheric conditions. This process is very expensive, and that's why monocrystalline solar panels are also expensive, whereas polycrystalline ingots are manufactured by directly casting melted polysilicon crystals in a dedicated crucible. So silicon crystals have different structures and orientations. Monocrystalline silicon ingot gives us monocrystalline solar cells, whereas polycrystalline ingot gives polycrystalline solar cells. Or in other words, monocrystalline cells are made out of a single crystal of silicon, whereas polycrystalline solar cells from several crystals of silicon melted together. You can recognize them by the shattered glass look given by the different silicon crystals. The higher efficiency of monocrystalline solar cells can be attributed to the uniform structure of silicon atoms inside monocrystalline silicon. During the ingot making, boron is added, which gives the silicon positive electrical polarity. This can be termed as p-type doping. Polycrystalline ingots are usually in square shape, whereas monocrystalline ingots are cylindrical because of the production method. After the ingot has cooled down, grinding and polishing are being performed, leaving the ingot with flat sides. The next step is wafer manufacturing. The silicon ingot is sliced into thin discs, or we call it wafers. A wire saw is used for precision cutting. The thickness of a wafer is similar to that of a piece of paper. The optimum use of this expensive monocrystalline silicon demands, instead of slicing it into a square which could be inscribed in a diameter of ingot, but to make them slightly larger, a rectangle with chamfered corners. That way, we waste less of the material in cutoffs. The following processes will convert a wafer into a solar panel capable of converting solar power into electricity. In an oven-like chamber, phosphorus is being diffused in a thin layer over the surface of wafers. This will charge the surface with negative electrical orientation. The combination of boron and phosphorus will cause a p-n junction, which is critical for the proper function of a photovoltaic cell. Because pure silicon is shiny, it can reflect the sunlight. To reduce the amount of sunlight lost, an anti-reflective blue color coating is put on the silicon wafer. The blue color is given on purpose to ensure the conversion of solar energy to electricity. The coating will facilitate the absorption of sunlight rather than reflecting it. Each of a wafer is being treated and metal conductors are added on each surface. These conductors give the wafer a grid-like matrix on the surface. This is how monocrystalline or polycrystalline solar cells are made. Thanks for watching.